Hi, my name is Andrew Burkhead. My research is called the lower temperature limits of circadian rhythms of phototaxis in Chlamydomonas reinhardtii. I work with Dr. Jacobshagen in her lab, and this project has been mostly done in the spring of this year. So I am an honors college student, class of 2023. Like I said, I've been a researcher since January. The organism we are using as a model is Chlamydomonas reinhardtii. It's very useful in circadian research, largely, in fact, due to its very similar sleep-wake cycle to humans, uh, in that they're both about 24 hours. The reason for that is because they're they have to acclimate to the same condition of the sun rising and falling, uh, which is a fairly obvious reason. Also, the organism has a fairly measurable phototaxic response, meaning when it moves towards or away from light, we can measure that and get very good results about whether there's a rhythm occurring and whether that rhythm is a part of the sleep wake cycle. The organism is also easily grown in culture. Uh, in 1 to 2 weeks, we can get exponential growth. So very easy to use, very easy to grow. So we're looking at the lower temperature limits of when a circadian rhythm can be regulated in the organism. So we're kind of looking for a breaking point, a point where the temperature is high enough so that the cycle can occur for the duration of our experiments. We find this by measuring the temperature and period of the rhythms and comparing the two. So what temperature can a rhythm period occur? We hypothesized that this would be very low, between 2 and 4 degrees Celsius, maybe even lower. That's where we were very surprised by our results. So our experimental design, we tested between a temperature window of 0 and 10 degrees. We thought the limit would be somewhere in there. The strains used, CC6090, CC124, and CMJ030. We just kind of use a variety of strains because they may react differently under different conditions, and we just wanted to kind of get them all in there so we don't have any odd results just because of it's only a single strain that's acting that way. We use constant darkness, meaning that when the phototaxis was measured to determine if a rhythm was occurring, they were in constant darkness. This was important because we wanted to know if a rhythm could be regulated without a light or source of sunlight or anything like that at that low temperature. The growth media used was TP and HSM. The particulars of those don't really matter. We just kind of use both of the same reason we use a variety of strains, just to get that variety, just in case one performs different under different conditions. So the TP medium and DD, that's the constant darkness condition. Light cycle equate to higher levels of phototaxis, or they have in the past. Previous findings also show that as you increase temperature, you get an increased period of rhythm, but also a higher standard error, so it cannot be replicated as much. The temperature of our experiments presented here are 4, 6, 8, and 10 degrees Celsius. We started at 4, and no rhythm was showed, as you'll see soon. So we kind of had to go higher, and we didn't really expect that. The duration of our experiments were 120 hours, or 5 days. Like I said, we're looking for that breaking point in phototaxis, that movement towards the light. Where is it moving towards the light in a cyclic form? When is it not? At what temperatures those two things are occurring at? We did this by measuring either the average period or rhythm completion percentage. So depicted in this graph here is what our machine spits out after the 5-day cycle. As you can see on the x-axis here is time, 5 days. So ideally, we would get 5 circadian rhythms if 100% completion percentage is shown. And here on this axis is measured the amplitude of phototaxis. So that change in phototaxis when it's traveling high in a high manner towards the light, very often that would be this peak here. And that would be when it is, say, like high noon, prime time to be awake. So we measure the period by taking the difference between the time it takes between these two peaks here, averaging it out for all the peaks of that sample. We measure the completion percentage by taking the total number of hours that a rhythm occurs under and dividing by the total experiment. So this would be somewhere between 50 and 60% rhythm completion. Also, in each graph is one strain of one media of one age. So these are all the same samples. It's just like they're just replicates basically. So experimental limitations: the maximum amplitude plateau at 5 degree or at 5.0 on the graph. So anything above that cannot be measured. Also, low cell concentrations have been an issue. If the cell concentrations are too low, phototaxis can't really be measured. So at 4 degrees, we found little to no rhythm, as you can see here. No cyclic response in phototaxis, just really straight lines. Did have some weird stuff going on here, but nothing cyclic. At 6 degrees, we had also little to no rhythm. Kind of got the start of some kind of circadian rhythm here in the 1690 strain and in the CC124 strain here, but no complete rhythm, not even one whole complete rhythm. So the results at those two temperatures, no really rhythm, nothing significant in the CC124, CC1690, or the CMJ00 strains. Some samples started to show rhythm, as I said, but then quickly leveled off, showing low completed percentage. At 8 degrees Celsius, we got quite different results. Beautiful rhythm here, 5 complete cycles shown in the CC124 strains. Beautiful rhythm. In CC1690, we got major rhythms, but they leveled off towards the end. They could not sustain that circadian rhythm at that 8 degree temperature. CMJ030 strain here didn't get anything really, similar to the 4 and 6 degree experiments. So that no rhythm shown on phototaxis in the CMJ030 strain was likely due to low cell concentrations, due to errors in inoculation of the sample into the media. So that kind of interfered with our process there. 100% rhythm completion in many samples, the CC124 specifically, as I previously stated, and significant rhythms of phototaxis for sure. At 10 degrees, we got many really similar results. We've done this one before, so we knew what to expect. CC1690, CC124, 100% rhythm completion, as you can see in this graph, best depicted. This kind of you can still see the cyclic response here in phototaxis, but there's kind of some bleeding going on. That's just due to errors in where certain samples were placed in our machine. CMJ030 strain here showed rhythm, 100% in some cases. That was because our cell concentrations got higher and as we improved throughout the semester. So significant rhythms at 10 degrees. CMJ030 samples showed significant rhythms as well, unlike the earlier temperature tests. So you can see this clear division between the temperature at 6 and 8 degree experiments. Period goes from 0 to 24.4 and 0 to 21.4 in the CC124 and CC1690 strains respectively. This here is obviously insignificant because, like I said, low cell concentrations, so we aren't completely sure about that strain. So that limit is likely somewhere between that 6 and 8 degrees Celsius point. We aren't really sure why the organism can't show rhythm at 4 and 6 degrees Celsius. It's either because the organism can't swim at such a low temperature, or because in and of itself, the organism can't regulate a cycle, which would make our results more significant. If they can't swim, that's an error in measurement. We really just don't know if they can show rhythm. A significant increase in rhythm completion percentage at 8 degrees, as you previously saw in the graphs. Rhythm completion shown at 10 degrees Celsius in most cases, 100%. So why was there no rhythm? Either they cannot swim or because they're unable to regulate the cycle. That's a point for future study. We definitely want to look at the organism under a microscope at low temperatures and see if it's swimming. That will make our results more or less significant. So use a smaller window as well. We want to kind of get that smaller window more between 6 and 10 degrees Celsius to find out specifically where that change is occurring. Also, we may in the future determine if prior to testing low temperature acclimation would help the organism respond better. This entails placing the organism at the temperature it's going to be tested at beforehand, before putting it in the Phototaxis measuring machine, and see if that helps any at all in regulating a sleep-wake cycle. So that's all I have for you. I'll take any questions now, or if you don't have any, thank you for your time.